Okay, let's do two more examples of exact differential equations. So here's our dE, 2xy squared minus 3 dx plus 2x squared y plus 4 dy equals 0. M is the stuff in front of dx, so that's 2xy squared minus 3. N is the stuff in front of dy, 2x squared y plus 4. To check and see if this is an exact dE, we take the mixed partials. So this guy's in front of dx, we take his partial with respect to y. This guy's in front of dy, take his partial with respect to x. If you get the same thing, you've got yourself an exact dE. So check these on your own. You should be able to see you get 4xy both ways. That means this is an exact dE. Then to find this higher order function we call f, we integrate each one of these with respect to the guy beside it. So the antiderivative of m dx would be antiderivative 2xy squared minus 3 with respect to x. Remember, y is a constant here. So integrating, we get an x squared over 2, which cancels that 2. The y squared just comes along for the ride. Minus 3x, plus possibly, maybe not, but possibly some additional function of y. We play the same game with the other guy, the antiderivative of n dy. So antiderivative of 2x squared y, the 2x squared is just a constant as far as y cares. So that's just a number times y. Antiderivative would be that number times y squared over 2. The 2 cancels. Antiderivative dy of 4 is 4y plus potentially some function of x. Notice both of them gave us this guy. So I just write that down. Then I write down all the other stuff. Oh, I've got that extra 3x. That was that h of x I was looking for, that negative 3x. I see a 4y. Oh, that was the g of y that was missing from up here. Okay. Now, again, you should check and make sure. Check that this guy's full differential, remember the differential is partial respect to x dx plus partial respect to y dy, you should check that this, doing this, gets you the left-hand side up here. That's what makes this an exact dE. The left-hand side is the full differential of this function, capital F. We're told in our dE that that full differential equals 0. The only way a full differential can equal 0 is if the function is actually equal to a constant. So we set the function equal to a constant. And this is our implicit solution. We're not even going to try to solve that explicitly. We're okay with implicit solutions on these. Okay, one more. We've got this, it turns out to be an exact dE. Probably could have guessed that. We're going to use it to solve an initial value problem. So here's my dE. Here's m in front. Here's n in front of the dy. Take the mixed partials and see if they're equal. Partial m respect to y, check that on your own, is 2x plus y. Partial of n respect to x, you get 2y plus 2x. Well, that's the same as this. Those are equal. Yay! So this is an exact dE. So that's just the checking part, checking the mixed partials. To find capital F, integrate both of them with respect to the guy beside them. Integrate m dx, integrate n dy. So the antiderivative of m, antiderivative of this will be x squared plus 2yx plus possibly some function of y. Okay, that wasn't correct. I've fixed it now. So the antiderivative of m dx will be antiderivative of x plus y squared dx plus potentially some function of y. So let's expand that out. X plus y squared would be x squared plus 2xy plus y squared. We're integrating that with respect to x. We get x cubed plus x squared y plus y squared x. Check those details. Make sure you believe that. Plus potentially some function of y. We play the same game with n, the antiderivative of n dy. Okay, I'll go through this one slowly. We're integrating with respect to y, so x is a constant. 2x just comes along for the ride. Antiderivative of y is y squared over 2, which will cancel this 2. We just get xy squared. Antiderivative of x squared, that's just a constant. So the antiderivative of a constant dy, we just pick up a y. Antiderivative of negative 1, dy is just negative y, plus potentially some arbitrary function of x. Okay, now to find f, write down all the things we have in common. Both of these potential solutions have an xy squared, so I'll write that down. Both of them have the x squared y, I'll write that down. Then I'm missing potentially some function of y. Oh, there it is. I got it in the other one, the negative y. I'm missing potentially some function of x. Oh, here it is. I got it in the first one. So write those down. Now, let's check just to make sure we got this right. Let's check that this guy's differential is our dE. So if we take his partial with respect to x, we should get back to m here. We should get x plus y squared. So let's check that. We're looking for x plus y squared. If I take his partial with respect to x, partial with respect to x here will be y squared plus 2xy plus x squared. That's what we were supposed to get. That's x plus y squared. Okay, what if we take partial with respect to y? We would get a 2xy, an x squared, and a minus 1. That's exactly what we were supposed to get. So this is correct. This is our function f. The next step here is always just set that equal to a constant and you're done. That's our general solution right there. Set f equal to a constant. There's the general solution. We want that subject to, that says st, subject to y of 1 equals 1. So we just plug in a 1 for all of our x's and a 1 for all of our y's. And we get this. That's 1 minus 1. Those cancel. So we get 1 plus a third. C then is 4/3. So our particular solution, the solution to this initial value problem, is C equals 4/3. So we just set the whole thing equal to 4/3.